Okay, so we're going to start Module 6, which deals with functions and inverse functions and eventually exponential and logarithmic functions. So the first section, we're going to talk about functions, composition, and inverse functions. So function notation we've seen before. Function notation is typically something that looks like f parenthesis x, which is read f of x. And this is just a notation to express an equation as a function. So in a function which has an input and an output, f of x just represents the output. So if I look at an example, if I say something like f of x equals x plus 2, that's really the same thing as saying the equation y equals x plus 2, where this f of x is just really shorthand for y. Y is our output, x is our input. So when you think about our first thing we're going to talk about in Section 6, kind of new thing, is what's called a composition of functions. A composition of functions is first of all denoted like this. So a composition of functions is taking the function value of another function. So if we think of our functions as f of x and g of x, then we can think of the composition f composed g. So this little open circle is kind of our representation of composition. F composed with g is really the same as f of g of x. So what that means is we will plug in g of x for all x's in f of x. So everywhere we see an x in f of x, we'll put in the function g of x. That is what a composition is. If you think of composition in like English or something, it's putting things together, which essentially is what we're doing with these two functions. So let's look at an example. I have two functions here. I have f, which is f of x, which is 3x squared minus 4, and I have g, which is negative 2x squared. So if I think of the composition f composed with g, this is really the same as f of g of x. So what we're going to do is we're going to take g of x, which in this case is negative 2x squared, and I'm going to put it into the other function everywhere I see x. So in this case, that's going to make the composition 3 times negative 2x squared minus 4. Oh, pardon me. 3 times negative 2x squared minus 4. So if you kind of look at just this part, this is where there used to be an x in f of x, and we put in that other function g. So if I simplify that, we know negative 2x squared, well, negative 2 squared is going to be positive 4. X squared squared, we can use our power rule, which we know is x to the 4th minus 4. 3 times 4 is 12. X to the 4th minus 4. So this composition of functions gives us another function. So if we look at the next one, it's really the same problem except for you notice g and f are reversed. So this really is saying g of f of x. So over on this first one, we plug g in for f. In this case, we'll plug f in for g. So everywhere I see an x and g of x, I'll put the f function in. Whatever is on the inside, that's what gets plugged into the other. So the g function is negative 2 times x squared. So instead of that x, I'll put 3x squared minus 4, which is my function of f. So now doing our algebraic simplifications. We know 3x squared minus 4 squared is 3x minus 4. 3x squared minus 4. So I'm just writing it twice. And then I'm going to FOIL those two things. So that's going to be 9x to the 4th. Then it's going to be minus 12x squared. Minus 12x squared plus 16. I can put those two negative 12x squareds together, so it'll give me negative 2. 9x to the 4th minus 24x squared plus 16. So finally, the last thing I can do in my simplification is I'll just distribute this negative 2. So the composition is really pretty simple. You put them in, and then it's just your algebra skills that you have to take over with. So negative 18x to the 4th plus 48x squared minus 32. So you'll notice the two compositions, when I switch the order, F composed with G versus G composed with F, much, much, much different answers. Let's look at another example. Here we have a little simpler functions. We have f of x equals x plus 3. And we have g of x equals 2x minus 7. So these are both linear. So first we'll do f composed with g. So that's f of g of x. That means we're going to plug the g into the f. So that's going to be, it says x plus 3 for f, so it's going to be 2x minus 7 plus 3. And again, I'm plugging the g into the x for the f. So if I simplify that, that's going to be 2x, negative 7 plus 3 is simply negative 4. Okay, if I look at the next one, I have g composed with f. So g composed with f is going to be g of f of x. So that's where I want to plug f in for g. So the g function is 2 times x minus 7. So I'm going to put that x plus 3 in for x. I can distribute my 2. So 2x plus 6 minus 7. 6 minus 7 is negative 1. So if you really remember what a function is from Algebra 1, a function is a relation in which each x corresponds to 1y. If you recall, we also remember that graphs of functions pass the horizontal line test. Or pass the vertical line test. A little ahead of myself. So if I have a graph with a bunch of points, so in this curve, this is infinitely many points. Point, all over these places. So we want each x value to have only one y value. So if I look at this x value, let's call it 1, it only corresponds to this y value. So this point, that x only has one y value. So this is a function. Vertical line test says if any vertical line hits it only once, which this does, it's a function. Something that wouldn't be a function would be something, say, like a circle. So if I take this value here, this x, then this x actually has two y's that would make it for the same x. If we call this x1, this could be 1, 1, and 1, negative 1. So this is not a function. And if you think about our vertical line test, if you take any vertical line, if it hits the function if it hits the relation twice, it's not a function. Now, for our basic understanding of functions, it's just good to be a function, but what that'll do eventually is open up a lot of different properties that will hold only to functions. So an extension of our regular functions is a one-to-one function. So a one-to-one function is going to be a function where each x corresponds to a unique y. So no other x can be with that y. So, for example, if I say if I say what is your social security number, so my social security number would relate to only one unique number. No one else would have that social security number. So one person has one number. So if I have one x, say the x value I have is 2, and that corresponds to, say, a y value of 3, then no other x value can have a y value of 3. That x of 2 is the only one that can have that y value, as an example. So as I almost said earlier, there is a special test for this, which is a horizontal line test. So the horizontal line test says if any horizontal line intersects the graph, or intersects a graph, at most once, then it is one-to-one. And really, the whole reason we bring this up is when we start talking about inverse functions, we really need to have the function be one-to-one to have what's called an inverse function. So if I have some graph, let's say something like this, every horizontal line has to hit it only once. Well, this horizontal line hits it 3 times. So we would say this is not one-to-one. Because if you think of this y value, there are 3 different x values that have that as a y value, meaning it's not unique. Okay, so let's look if this function is one-to-one. So we said a function is one-to-one if it passes the horizontal line test. So if I take a series of horizontal lines and it only hits once, which these do, then the function is one-to-one. So we can simply say f of x is one-to-one. And that will mean something very important to us here soon. So we look at the second one. We have g of x equals 9x to the 6 minus 7x to the 5th minus 4. And you can see I just graphed this in Desmos. And if you look at this guy, if I take some horizontal lines, well, it definitely hits twice. So we can say this function, g of x, is not one-to-one. And again, being one-to-one will help us have one really cool property. So why we kind of do compositions and we do one-to-one functions, it all kind of leads to this concept of an inverse function. Okay? Now an inverse function in its kind of basic form can be really easy to think. If I decide to make a function where I'm going to add 10 points to everyone's score, to your grade. So everyone's grade goes up by 10 points. Well, the inverse function is a function that's going to undo what we just did. So if I want to get back to where I started, I will, of course, subtract 10 points. So if we start with some grade, let's say you had a 50, and I added 10 points, that gets you to a 60. But then if I take that 60 and subtract 10, you're back to the original 50. So the inverse function is going to be one that's going to undo one another. So our formal definition of inverse function, we could say any function that is one-to-one, so it has to be one-to-one, that's why we had that definition, has an inverse function and we denote this f to the negative 1 of x. This is read f inverse of x, where that if we take the inverse function of the function, it always gets us back to x. Okay? So this is kind of shorthand for saying that if I plug something into one function and then I plug that output into the inverse function, it gets us back to where we started at. Okay? So let's look at an example of an inverse function. Okay? So in this problem we have a function 3x minus 11. So it says if f of 2 equals 5, so f of 2, remember, just means x equals 2, so I'll show you how we got 5. So it's 3 times 2 minus 11. Well, that's 6 minus 11, which is negative 5. Okay? So we started with x equal to 2. I plugged it into this function, and we got out negative 5. So what we can know about its inverse function, so it has this magical inverse function, and what I know about the inverse function is if I take this value that I had at the end, which is negative 5, if I put the output value, what I had at the end, negative 5, I should get back to where I started, which was 2. So this function kind of flows this way, plugs 2 in, gets negative 5. Well, the inverse function takes negative 5, plugs it in, and gets 2. But together, you see, they basically get you right back to where you started from. Now, there's a couple really simple ways we can see if inverse of two functions are inverses. The algebraic way, we can say that f of x and g of x are inverses if f composed with g of x is the same as g composed with f of x. So they have to be the same. Remember earlier problems, they weren't the same. They have to be the same and they both must equal x. So if you do both compositions and they both equal x, then the two functions are considered inverses. They would undo each other. The other way to check is we can also say a graphic check. We can say f of x and g of x are inverses if their graphs are symmetric to the line y equals x. So if you remember what y equals x looks like as a line, it just looks like something like that. So if the graphs are symmetric about that, they're mirror images of one another, then we can say they are inverses. So let's look at an example where we can show two functions are or are not inverses, and then we'll kind of show the benefit of that. So I have two functions. I have f of x equals 3x plus 4 and g of x equals 1/3 x minus 4/3. So if I want to algebraically check, I'll do their composition, f composed with g of x, which is f of g of x. That means since g is on the inside, we'll plug it into f. So this will equal 3, parenthesis 1/3 x minus 4/3 plus 4. If I distribute the 3, I'm going to get 1x minus 4, because 3 times 4/3 is just 4, plus 4, which cancels and leaves us just x, which is good. We need both of these to be equal to just x. This is not enough, though, so I also have to do g composed with f of x, would just be the opposite. So that's g of f of x. So that would be putting f into g. So that would be 1/3 times 3x plus 4 minus 4/3. So when I distribute, I get 1x, because 1/3 times 3 is just 1, plus 4/3 minus 4/3. So this would also just equal x. So based on that, we know f and g are inverses. Now the cool thing about being an inverse, let's pick any number. Let's pick an x of 1. Well, if I plug 1 into this first function, I get 3 times 1 plus 4, which is 7. So I plugged in that and I get 7. Well, now if I take this 7 and I plug it into the other function, which is its inverse, 1/3 times 7 minus 4/3 is 7/3 minus 4/3, which is 3/3, which takes us right back to 1. The key thing here is I started with 1, and when I go through both the function and its inverse, I end up right back where I started. Alright, so here's another way to check them. Now, we could do the algebraic check, that's fine. But what you can also see here is I have graphed the two functions and I graphed the identity line, which is y equals x here. Now if you see that these two graphs are symmetric to this line, they flip over one another. Kind of a really cool point about inverses, if you look at this point, which is on the red line, which is 0, 4, if I look on the blue line, then I have 4, 0. They're switched. So x and y always switch in inverses. If you remember your geometry, being symmetric to the line y equals x is why the points switch, but in inverses they are always symmetric to this line. So if they can fold over neatly on each other onto one another, then we can say they're inverses. Okay, so the last thing we're going to do in this section is we now kind of know what an inverse function are. We kind of can prove two functions are inverses, but sometimes you want to know what the inverse function is. Some are pretty simple. If I take, say, f of x equals 2 times x, multiplying by 2, then the inverse would simply be dividing by 2. Because you know multiplying by 2 and then dividing it by 2 gets you back to where you started. The general methodology for finding inverses, we will just switch x and y and resolve for y. Okay? Switch x and y and resolve the equation for y, and that gets you your inverse. Now, one interesting thing, you look at this, I have f of x equal negative 2x minus 7, I have no y. But if you recall, we said f of x is just the same thing as saying y in our function notation, so I can simply write it like this. So in the process of finding my inverse, I will switch x and y, so x equals negative 2y minus 7, and I will now solve for y. So I'll add 7 to both sides. So it's x plus 7 equals negative 2y. And then I'm just going to divide everything by negative 2. So that's going to give me negative x divided by 2. I have 7 divided by negative 2, which is minus 7 over 2. And that's equal to y. So that is our inverse function. So if I want to write it formally, I could say f inverse of x equals negative x over 2 minus 7 over 2.